Okay, so we are talking about group. We have seen the order of an element. Now we will talk about cyclic group, but before that let us start the concept of subgroup. Okay. So, how to define the subgroup? This is the definition. Now, let G be a group which is basically G is non-empty. And let H be a non-empty subset of G, where H is also non-empty. Okay, so this is our G group, G set, this is our H set. So, H is a subset of G. Okay. So, now we define the so G is having this operator. Now we define the induce operator on of this star on H. So, how to define? Now, this star is said to be stable star is said to be, this is G, star is said to be stable, or in other words this is called close also. Close under or sorry H is said to be stable or close under star if and only if you take any two element A B from H, this is also an element in G. And we know if if you take two elements from H, A B, now these are also element of G. So, A star B will be element of G, this we know because G is a group. So, the closure property will satisfy, this is okay, but it need not be in H again, but we want this to be in H. So, that is the stability, that is called stable or close under this. If implies A star B is also in H. So, that means H is close under this star. Okay. We know this will happen because this is a group, G is a group. So, if we take any two element A B, then A star B will be belongs to G because of closure property, but we want to be this property is in H also. Okay. So, then we can say this H is stable or close under star, and if this is close under star, then we restrict our operator star on H only. If we just think this we are operating this star on H only, then we can say this star we can have another operator, this is some different operator. This is basically what? This is a restriction of star on H. Okay. This is basically the operator star, but the elements are coming from H. This is a binary operation, element are coming from H. So, this is the induce operator on this. Okay. Induce composition on this. Anyway, this also you can write at star instead of this. Now, if this is from a group, this along with this induce operator, if this is a group, then it is called a subgroup, because this is a subset, then it is called a subgroup of G. Okay. So, let us formally define this. So, let this is the definition of subgroup. Let G be a group, non-empty group, and H be a non-empty subset of G. subset of G. Now, if H is also form a groove, is a groove under the under star, where the star is the induce operator on H only. Okay. Star is induce, or we can say this is different operator, but it is basically the same operator. Only thing we are restricting our domain to be H only. Induce where this is where this is the induce operator or induce composition, this binary composition, induce composition of star. Okay, then H star, we can say star, because when we say star we have to be little careful here, because star is usually the binary composition on G, but here we are restricting ourselves on H. Okay, so that is why better to use some other symbol, other this small o kind of symbol to indicate that this is a operator which is induce operator of star on H. But anyway, we can just this, or sometimes we can just write star this. This is also fine. Only thing, when we write this, we have to be careful that this is our domain is in from H only. Then this is called a subgroup of G, because this is a subset and this subset is also forming groove under that induce operator. So, then it is called a subgroup of G. So, this is the definition of subgroup. Now, we want to have some example on the subgroup. Okay, so, the obvious subgroup is the singleton set E. So, this is basically our G. Now, we say and we have a star operator composition on G. Now, this is a subset on this. Now, we talk about the induced subset. So, if this is also if this is a subgroup, this is a groove, and then we call this is a subgroup of G, and here this star is induced, because for this star we take two elements from this. So, this star is basically H. So, domain is changing basically, it is a composition on, it is a binary composition on H. Okay, so, now let G be a groove. Now, let E is be the identity element. Identity element of G. Now, we write as this way, because now we have another set E G, identity element of G. Then the singleton set, this is, if we consider H to be the singleton set E G, then this will form a groove. Then this is a subgroup, this along with this star is a subgroup of G. We can easily check that, because closure property is satisfying. If you take this star, this, it is itself, associativity is also okay, identity is already there, this is the identity. Then the inverse, the identity element has his own inverse, I mean it is inverse itself. So, this is a subgroup. So, this is the singleton subgroup. Now, we take some example of other subgroups. Now, if we consider say this is examples of subgroups. Say we consider the group G to be say Q plus. Okay, our set is set of all rational number. Now, if you take subset Z from Q, this is a subgroup of Q plus. This is one example. Another example is say if we take just Q, if we omit this, then this will form a group. Or if we take just this Q is a subgroup of R, set of all real number. This Q is the set of all rational number. Okay. Now, we talk about, there are many other examples also. We can take the we can take some example like symmetric group. Say symmetric group of S3. Symmetric group S3. S3 means this is the set of all permutation of order 3. Okay. So, how to define this? So, S3 consists of this permutation. So, this is 1, 2, 3, this is the identity permutation, then this is the 1, 2, 3, this is going to 2, 3, 1, and then 1, 2, all possible permutations. So, how many permutations are possible? So, there are 3 elements. So, factorial 3, 6 permutations are possible. So, let us just write all possible permutations. 3, 1, 2, this is denoted by P 2, P 3 is basically 1, 2, 3. So, this is P 1, 1, 2, 3, then 1, 3, 2, and then P 4, 1, 2, 3, it is basically 3, 2, 1, and then P 5. So, it is starting from 0. So, there are 6 permutations, 3, 2, 1, and this is basically 1, 2, 3, this is basically 2, 1, 3. So, these are the set, this is the set, this set is denoted by S 3. So, this is the set of all possible permutation on 3 element 1, 2, 3. Okay. Now, if we write this as a cycle, we know that every permutation can be written as a product of transposition, like cycle of order 2. First, let us try to write this as a cycle. So, this is basically how to write this as a cycle. So, 1 is going to 2 and 2 is going to 3 and again 3 is going to 1. So, this is a cycle of order 3. Now, here, so this is basically what? This is again 1 is going to 3 and 3 is going to 2 and 2 is going to 1. And here this is basically 2 is going to 3 and 3 is going to 2. And here it is basically 1 is going to 3 and 3 is going to 2. And here it is 1 is going to 2 and 2 is going to 1. So, these are the cycles. So, this is the cycles of length. Now, we know this is a group under the composition of 2. These are all bijective mapping and this star is the composition of 2 bijective mapping. So, if you take two permutation, if you compose it, it will give us another permutation of same order. So, it is also a composition of two bijective mapping is bijective mapping. So, we know this is a group, this is a group. Now, we want to have a subgroup of G of this group. So, this is our G group. Now, if you take all the even permutations, like these are the even permutations, because this will be again written as product of all odd permutation, these three. So, now if you take A 3, so this is basically no sorry, if we take all the even permutation, this is the odd permutation. Odd permutation means if it is written as product of this. Now, even permutation is, so this can be written as 1 3 and then 3 1 like this. So, now this is basically a even, these three are all odd permutation and these three are even. So, what are the even permutation? Like identity permutation 1 2 3 1 2 3 and then this one, this P 1 and then another one is basically this one P 2 1 2 3 3 1 2, this is P 2 3 1 2. So, this will be a subgroup of this. Okay. This is a because this we can show again, this is a group of G. So, this is called subgroup of, this is a subgroup of this S 3. Okay, this is another example of subgroup. Now, we will talk about some of the properties of this. So, we will come back to this again. Now, first property is suppose G is a group and H is a subgroup of G, okay, is a non-empty subgroup. Subgroup of G. Now, it is the theorem is telling if G is abelian or commutative, G is abelian group, then this will be also an abelian, group. Okay. Why? Because if G is abelian means what? A star B is equal to B star A for all A B. Now, how to show H is abelian? If you take any two element, say CD from H, then we know C star D, they are also element in G. So, C star D will be D star C, and this is true for all C D belongs to H. So, this implies H is also abelian. Abelian group. But the converse is not true. That means, if we may have a subgroup which is abelian, but the original group is not abelian. For example, this A 3 is A 3 we can easily check, this A 3 is a abelian group. Okay, this is a subgroup of S 3, but S 3 itself is not an abelian group. S 3 is not commutative, because in general the bijective mapping is bijective composition. Composition is not a commutative operation. So, this is an example where we have a subgroup which is abelian, but the group is not abelian. Okay. So, now we talk about some other properties, like if they have a same inverse, they may not have two different inverse or identity element. So, we have this group G and we have the subset H which is also subgroup under the same operation, but induce operation. So, this is also a subgroup. Now, our claim is this identity element of G must be the identity element of H. So, they have same identity element. So, that this is another theorem. So, ID of identity element of G must be identity element of H. So, this is the theorem. So, they may not, we should not have two different identity. In other words, the identity element of G is belongs to the H. Okay. So, how to prove this? So, to prove this we can just suppose, so we have to prove this. So, suppose they are not same, they are different. So, we have a identity element here and we have a different identity element which is not in H, say, or maybe in H, but they are different. Okay. So, we have two different identity element. Now, if we have this, then what we can say? We know this E g is the identity element of this, then we can simply say H star E h is basically equal to E h star h, which is basically H, and this is true for all H. Now, if we apply both side by E g, E g, which is basically H star E g. Now, this is an element in G and this is the identity element of G. So, if we apply any element with the identity element, this will give us the that element. So, H star E h is same as H star E g, and this is true for all H. Now, by cancellation property we can just say E h equal to E g. So, this is the this is how we convince that. So, they have the same identity element. So, the identity element will belongs to the H only. They have the same, they share the same identity element, which is we know the identity element is unique in the group. Okay. Now, the inverse, say inverse is also, now inverse we cannot say, because see if we take an element over here, then A inverse has to be belongs to H, and we know that is the unique element. Okay. Now, we talk about some necessary and sufficient condition to be a subset, non-empty subset to be a subgroup of G. Okay. So, this we write in a theorem form or lemma form. So, this is telling let G be a group and H is a non-empty subset. So, that means H is not equal to phi and H is called, H is a subgroup of G if and only if these two properties satisfy. So, A B belongs to H, this is the closure property. Okay. And the second property is A belongs to H imply A inverse belongs to H. So, this is a theorem where. Okay. So, now how to prove this? There is two part of this theorem, necessary part and sufficient part, if and only if. Now, first we assume that this is a subgroup. Now, suppose this is the first part, let us suppose H is a subgroup. Then we show these two satisfy. Then this implies if we take A B belongs to H, this implies A star B belongs to H. for all A B because of closure property. Okay. Now, also since this is a subgroup, then if A belongs to H, then A must have a inverse, because it is a group, basically it is a group and it is a subset, that is why it is called subgroup. So, this implies A inverse belongs to H. So, every element has the inverse in a group. So, H is a group. So, every element has the inverse. So, these two properties satisfy. Now, the other way, converse. Converse means, suppose H is a subset, non-empty subset, and this true is true. Converse, suppose this true is satisfying, then we have to show that H is a subgroup. Okay. So, now first property is telling us the closure property. If you take any two element, then they are A star B belongs to H. So, closure property is satisfying. Now, this is closure is done. Associativity is also okay, because if you take any three element from H, they are also from, this implies, because H is a subset of G, then we can write, since G is a group, we can write this, because G is a group. So, in the group the associativity is satisfied, G is a group. So, star is associate in G. So, they, if A, B, C are in H, so they will be also in G. So, associativity is straightforward. Now, the identity element, we need to check the identity element whether this belongs to H or not. So, existence of identity. Okay, now, if we take, we know that if we take an element A, now just this implies A inverse also belongs to H. Now, if we take A inverse B to be A inverse, now we know this A B belongs to H means A star B belongs to H. So, this is nothing but A star A inverse, this is nothing but E. So, E belongs to H. So, the identity element of the group is also an identity element of the identity element belongs to H. So, E is the, so identity element of that group is same as identity element of this subgroup also. So, this is not yet subgroup, only three properties satisfy. Now, we need to check the inverse. Inverse is also okay, because from this result, because if A is belongs to H, then A inverse is also belongs to H. So, from this result we can say inverse is also exists. So, every element has the inverse. So, hence this is a group, H is a subgroup of G. Okay. So, we will talk about more on the subgroups in the next class. Thank you.